We're going to continue our conversation about electric forces. You'll remember that the last time we talked about how you could take Coulomb's law, which is how you quantify the force between two charges, and you can use that to build a system where one charge is being influenced by multiple charges. And you do that by just adding each of the forces in a vector environment using the component method. What we're going to do is continue with that idea, but now we're changing the circumstances a little bit. We'll still be adding multiple forces in one field and how those multiple forces act on one force, but we're changing the field a little bit. Now we're going to put a substance into the field. That substance is called a dielectric. I can't believe I so abysmally misspelled that and missed it. It is dielectric constant. The assumption up to this point is that the charges that we have been calculating are existing in a vacuum. And of course, that is not everyday existence. It does not typically happen in a vacuum. And so we're going to have to amend our thinking on what this actually does look like. So instead, we're going to talk about what is going to happen in a medium. It will always have a hindering effect. Think of the medium as an obstacle for the forces to overcome. If there's nothing in between the forces, then their push or pull is unmitigated. It's just bare and what it is. But if I put it in a medium, now it has the medium to contend with, and especially the electrical effects in the medium to contend with. And we measure that effect of the medium in a thing called the dielectric constant. And I spelled it wrong there too. Oh my goodness. Dielectric, D-I-E. I just have that in my head, I guess, this time when I said it. Dielectric constant for a given material is going to tell me how much is this going to influence the push or pull of charges in the same area. Again, it's always going to be a hindering effect. A dielectric is never going to make the pull or push greater. It will always limit it. It interferes with what's going on between the original charges because the dielectric material, which is, by the way, an insulator by nature, the dielectric material will become influenced by the existence of the charges in the field. And so they're going to start rotating and creating their own alignment of positives and negatives that again mitigate the actual force between the original objects. So K is the dielectric constant for a given medium. It is going to tell you to what extent is it influencing the force. It is a ratio of vacuum, the force that would exist in the vacuum, to the force that would exist in the air. Now the force that would the force that would exist in the medium, and air is one of the first ones I'll be talking about, but just generically in whatever the medium is that I'm referencing. Because the force in the vacuum will always be the greater of the two forces, always. Remember we said that when I put it in a medium, the medium is going to have a hindering effect on the force between those two charges. It confuses it. Those insulators are going to start rotating and changing direction, and they're going to become polarized. And in the polarization of it, those charges that exist in the polarized insulator are going to influence the effectiveness of the force that existed between the two original charges. And because this ratio is always going to be a bigger number over a smaller number, K, the constant, is going to be greater than 1. It is constant for a given material. It's not a universal constant. It's a constant for the material. And again, here is a list of the dielectric constants. And I want you to notice how that water has such an extreme hindering effect because water is such a polar molecule that it has a natural dipole moment in it that's not ever going to go down or go away. But that dipole moment is already there, and if it starts rotating, that's only going to make it all the more extreme because water typically, just when it's left alone and not in an electric field, has random direction to the polarity. It doesn't line up so that it's all positives on one side and all negatives on the other. But when you put it in an electric field, those polar moments in a molecule itself, they're going to start changing direction and lining up along the field. And when we talk about field, I'll talk about that a little bit more. I don't want to get into that too much right now. I just want to talk to you about the existence of a dielectric and the influence that it has. So you can see that air is almost, for all intents and purposes, you can call it one. Body tissue is going to be somewhat high compared to the other ones because it is made largely of water, but pure water is going to be a dielectric constant of 80. And keep these in front of you when you do your problems. You're going to want to see what these are. All right, where would you put K in a formula to show that it does hinder the force? So my original formula is lowercase k q1 q2 all over r squared. So if I have this formula where it's lowercase k q1 q2 over r squared, where am I going to put the capital K? I know that's very unfortunate. Where am I going to put the capital K to indicate that it's a hindering force and not a beneficial force? Think about that for a moment. Where would you put it? Okay, you're going to want to have it in the denominator because that will make the bigger that is in the denominator, the smaller my force is, which is exactly what happens. And so this is going to be our new working equation whenever we have the conversation of a dielectric in the problem. Then you're going to need to reference this chart and identify what the K is. I've had students in the past tell me how irritated they are with the fact that it's capital K and lowercase k. And yeah, I know that's annoying. You could make it easier if you wanted to by replacing lowercase k with what it actually is. It's 4 pi times the permittivity constant, the original permittivity, how much it allows this to be going through, the charges to be working through the environment. And if you multiply all that out, it ends up being 9 times 10 to the 9th, and then we just call it k, lowercase k. But if you want to get rid of the lowercase k and instead put in 4 pi epsilon naught, then you're welcome to do that. I think that's kind of a pain. It's 9 times 10 to the 9th and just leave it at the top. So lowercase k is 1 over 4 pi epsilon, which is permittivity, epsilon naught. And it equals 9 times 10 to the 9th. So it's easier to do this and call it 9 times 10 to the 9th than in the formula do this and call it 9 times 10 to the 9th. But it's the same either way. So I say stick with the lowercase k and the uppercase k and just deal with it. All right, so number 20 in the homework, let's go ahead and look at that. Number 20 in the homework says, and I've kind of got a little drawing there for you, but number 20 says, calculate the force between a sodium ion charge E and a chlorine ion charge negative E when separated by 2.8 times 10 to the negative 10 meters in air, and then when separated by the same distance in water. So the first one I did was in air, and it looks like this. And basically, here's my drawing where I have my two charges, and they're separated by 2.8 times 10 to the negative 2. I didn't put that in there, meters. And positive E is just 1.6 times 10 to the negative 19. When you see that written, remember that a positive E is 1.6 times 10 to the negative 19. Negative E is negative 1.6 times 10 to the negative 19. And if it's in air, the dielectric constant for air is 1.006. So we're just going to do the math with all of that. So it's lowercase k q1 q2 all over capital K r squared. I plug all the numbers in, and again I can go ahead and use just the 1.6 times 10 to the negative 19 squared because charges do not show up in my F sub q. And that's all taken care of in the direction that we deal with later. And then I threw in the 1.006. And by the way, if you do the math on this and just use 1, you would get 2.94 times 10 to the negative 9 newtons toward each other. My point with that is to say 1 or 1.006 doesn't really matter. I'm fine with you saying with this one, it is approximately equal to 1. And if you want to use 1 on that, we're not going to have a big difference in our answer, so go ahead. Then the second part of the question was, what is going to be that same force in water instead? So now we look at the dielectric constant for water, and it's 80. So it's the exact same equation, only this time instead of 1.006, I'm going to put in 80. And my new force is 3.67 times 10 to the negative 11 newtons toward each other. And the reason for both of them that it's toward each other is that I started out with opposite charges. One was positive, one was negative. So in both cases, the force is directed toward each other. I want you to notice how amazingly reduced the force is between the not in water and in water. It's by a power of 2, or it's reduced by 100th, and it's reduced 100 times. Is that a better way of saying it? This one is not quite 100 times bigger than this one is what I'm trying to say here. So notice how much the force is reduced in the water. Why? Again, it's because water is so highly polar, extremely polar. There's such a big difference in electronegativity between the oxygen and the hydrogen that the electron around the hydrogen spends most of its time around the oxygen, making it much more negative than the hydrogen. And because of that, it creates, it lines up its own charges in an electric field so that it actually interferes significantly between those two charges because there is a whole series of charges going on in between. All right, that is the conversation of dielectrics, and your homework tonight is going to be, give me just a second while I pull this out. I want to make sure I'm not going to assign more than I'm supposed to. And your homework is 20. I'm sorry, I just did number 20, so that won't work. So let's do 21, 23, 24, and 26. 21, 23, 24, and 26. And let me double check to make sure that's what I wanted. Yep, that's what I wanted. And if you have any problems with that, let me know. But it's really a continuation of what you did in this last homework. The only thing now is you're sticking a number in the denominator depending on the medium. It's not going to really change anything or make it more complicated. You're just adding that one factor to the formula. So you should be okay. Let me know if you need anything.